Welcome to The Explainer. Today, we're going to talk about the science behind something that's absolutely critical in material science. Adhesion. It's this invisible force that really determines whether a product is going to succeed or fail. You've definitely seen this before, right? Peeling paint, flaking coatings, cracked finishes. And look, this isn't just about something looking bad. It's a fundamental failure of the material to do its job. And that can lead to corrosion, damage, and total product failure. The reason that happens all comes down to a force called adhesion. So for anyone out there designing durable, high-performance products, understanding this force isn't just, a nice to have, it's literally everything.
All right, so how do we get a handle on this invisible force? In this explainer, we're going to unpack the basic science of sticking, we'll break down the three main theories that explain how it works, and then we'll see how they all come together in the real world to make coatings that actually last.
Okay, first things first, it's really important to get this. Adhesion isn't just one single thing. Nope. It's a powerful combination of different forces all working together, but on totally different scales. So down at the microscopic, the molecular level, you've got chemical forces. Think of them as these invisible little hands holding molecules together. Then, at the macroscopic or physical level, you have these big structural forces that act like anchors. A really strong, durable bond is almost always going to be a mix of both. And the strength of that final bond? Well, it depends on a bunch of key factors. It's kind of like a delicate dance between what the coating is like, what the surface is like, and even the environment where it's all happening. If you mess up just one of these, the whole system can totally fail.
All right, let's jump into our first big theory. This one is probably the easiest one to picture in your head. It's called mechanical interlocking.
The idea is actually super simple. The liquid coating flows into all the little pits and pores and valleys on a rough surface. Then, when it hardens, it's physically locked in. It's created thousands of tiny little anchors that are holding it on tight.
Now, for this microscopic Velcro thing to work, two things are absolutely essential. First, you need a rough surface. You need places for that coating to actually grip onto. And second, the coating itself has to be fluid enough to get into all those little nooks and crannies before it sets.
But, and this is a big but, surface roughness is a classic double-edged sword. Sure, it creates those super important anchor points, but it can also trap tiny bits of gunk like oil or dust or even little air bubbles. And all of that stuff is going to weaken the final bond. So the real trick is finding that perfect balance.
So what happens if your surface is perfectly smooth? I'm talking about something like glass. Well, mechanical interlocking is pretty much useless there. And that is where our second and much more powerful theory comes in, chemical bonding.
With this theory, we're going way beyond just physical anchoring. We're getting into the world of molecular superglue. We're literally talking about the atoms of the coating forming actual, real-deal chemical bonds with the atoms on the surface. This is, hands down, the strongest adhesion you can possibly get.
To be specific, we're talking about covalent bonds, and these things are incredibly strong. Their bond energies can go from 100 all the way up to over 1,000 kilojoules per mole. That is just a massive amount of energy holding that coating right where you put it.
Now this is what I think is so cool about this slide. It shows how modern coatings are actually engineered to do this. I mean, just look at the table. The resins in things like epoxies or polyurethanes, they're designed with these specific little parts, these functional groups, that are basically chemically programmed to hunt down and react with metal surfaces to form these super powerful, permanent bonds. This is intentional chemistry, and it's exactly why an engineer would pick one of these systems for the most demanding jobs.
Okay, on to our third theory. This one becomes really important when you're working with polymers, like coating one plastic with another. It's called the diffusion theory.
I want you to imagine two separate bundles of tangled up yarn. If you push them together, some of the strands from each bundle are going to cross over and get all intertwined with the other. That is a perfect way to think about what's happening here. These long polymer chains from the coating and from the plastic literally diffuse into each other, creating this inseparable, tangled-up layer between them.
Now, the key principle that makes this all possible is compatibility. You might remember that old chemistry rule, like dissolves like. It's the same idea. The polymer chains in the coating and the substrate, they need to have a similar chemical nature or solubility to even be willing to mix and get tangled up.
But this whole diffusion process, it's pretty sensitive. It needs the conditions to be just right. If it's too cold, the polymer chains are just too stiff to move around. If the plastic is too crystalline, they're already locked in place. And if the coating cures too fast, well, there's just not enough time for them to mix and mingle.
So there we have it, these three really distinct theories. But here's the thing. In the real world, they almost never work alone. So let's take a look at how they all team up to give us the complete picture of adhesion. Before we look at any specific materials, there is one universal, non-negotiable rule, and that is good wetting. Seriously, if your liquid coating beads up on the surface, instead of spreading out nice and smooth, it can't make intimate contact. And if there's no contact, then none of the other mechanisms, not mechanical, not chemical, not diffusion, none of them can even start.
So how does this all play out? Well, if we look at this table for a porous surface like wood or concrete, you can see the star of the show right there in the first column is mechanical interlocking. The coating soaks into those pores, creates a strong physical anchor, and it's helped out by some weaker secondary chemical bonds.
Now, let's switch over to a metal surface, like steel. The game completely changes. The main mechanism here becomes that powerful chemical bonding we talked about. Now, you can roughen the surface to help a little bit. It creates more active sites for those chemical reactions. But it's really the molecular glue that's doing all the heavy lifting.
And this right here brilliantly shows just how complex it gets when we're talking about plastics. For polymers like ABS, you can see in the top row, you get this powerful 1-2 punch of both diffusion and chemical bonding. But for a low-energy plastic like polypropylene down in the bottom row, those strong mechanisms just don't work. You're left with these really weak forces, these tiny temporary molecular magnets called van der Waals forces, unless you pre-treat the surface to make it more reactive. And that is exactly why some plastics are so darn hard to paint or glue.
So you see, really mastering adhesion isn't about just one theory. It's about understanding which combination of forces you need to leverage for your specific material. The big takeaway here is that this unseen science of sticking is absolutely fundamental to creating products that are built to perform and engineered to last. The only question left is, what are you going to build with this knowledge?